Hi, everyone. Today we're going to talk about lesson 7, which is on decomposition reactions. Okay, before we get into today's lesson, I wanted to take a minute and review the homework problems from our previous lesson, lesson 6 on synthesis reactions. So if we take a look, we had to do problems 4, 5, and 6. So in problem number 4, we have magnesium reacting with nitrogen to produce magnesium nitride. The formula for magnesium nitride is Mg3N2. That's because magnesium has a 2+ charge, nitrogen has a 3- charge. So in order to get them to balance out, we needed 3 copies of magnesium and 2 of nitrogen. For students who are just writing the names, we have magnesium, we have nitrogen, and then of course, when we write the formula for magnesium nitride, the ending on nitrogen has to change to that IDE ending. And again, this was a synthesis reaction. For the second problem, we had magnesium oxide reacting with water. So a metal oxide reacting with water produces a metal hydroxide. The charge on magnesium is 2+, so we needed 2 copies of hydroxide in order to figure that out. And then finally, our problem number 6, we had a metal oxide, a non-metal oxide coming together to form magnesium carbonate. I put the type of synthesis reaction over here. You don't have to show that. I'm just doing it so you can see where it's coming from. So as far as the names are concerned, we have magnesium oxide, carbon dioxide, and then our product is called magnesium carbonate. For problems 11, 12, and 13, again, we have a synthesis type 1, so 2 elements combining, lithium and nitrogen. Remembering, of course, nitrogen is in group 15, so it has a -3 charge. So lithium combines with nitrogen here in order to produce 2 lithium nitride. In example number 12, we have sodium combining with chlorine to produce sodium chloride. +1, -1 means we'll get 1 of each. And then we just have to balance this equation. So we get 2 sodiums plus 1 chlorine gives us 2 sodium chloride. Finally, number 13, I have dinitrogen pentoxide plus 1 water. We have a non-metal oxide combining with water, so we're going to get an acid out of that. So H+, our acid is NO3-, so H1 plus NO3-1 means we have 1 of each. If you're looking at how to balance this, we have 2 nitrogens here, so we need to have 2 copies of nitrogen here. 5 oxygen plus 1 more is 6, so we have 6 oxygen here, and then 2 hydrogen, 2 hydrogen. Okay. Let's start to talk about decomposition reactions. So as I mentioned, we have 5 different types of reactions. We covered synthesis, and now today we're going to cover decomposition reactions. So I'm going to start by going over the general equation for a decomposition reaction. So in our case, we have AX going to form A plus X. So AX is a single reactant, which is going to be a compound. It breaks down to form 2 or more elements or compounds. So A and X could be 2 separate elements, or they could be a compound, or they could be a mixture of a compound and an element. These definitions here should be right below the term on your handout. So there's a box there. Please copy that definition into the box. Okay, so I'm going to show you a bunch of different decomposition demonstrations, the first of which is going to be the decomposition of cupric carbonate. Here you go. So again, we're going to begin by lighting our burner. Goes without saying, but you never want to heat a closed container. So obviously this isn't just a test tube that has an open mouth, but you wouldn't want to heat a closed container because pressure would build up and then eventually that would explode.
So as we heat this cupric carbonate, I want you to pay attention to the bottom where the flame is touching. You'll notice that it's quickly changing color. Now, one of the things that you're not able to see is this decomposition involves the production of a gas, and we'll talk about what that gas is. Okay, so I'm going to turn this off. Down here, I'm going to show you the results of what's in there. So if we had more time, we would let this go for longer, but I pour this out, you're going to see there's a mixture of both reacted and unreacted cupric carbonate. So you'll notice if you look closely, there's still some green color, that blue-green color of the cupric carbonate that has not reacted. And next to that, you'll see, it looks like carbon actually, it's cupric oxide. So those are the two components that are there.
Okay, writing an expression for that demonstration, we're going to have CuCO3. This was our greenish blue solid. When we expose that to that intense flame, we basically are decomposing it by heating it. So it breaks down to form CuO, which is known as cupric oxide. This was the black powder that was formed, plus CO2, which is, of course, carbon dioxide. When we balance this equation, we'll wind up with coefficients of 1 across the board. Let's take a look at a second demonstration. In this demonstration, we decomposed hydrogen peroxide. So if we look at our formula for hydrogen peroxide, it is H2O2. When we decompose hydrogen peroxide, many people want to suggest that it breaks down into its two elements, hydrogen and oxygen. That is not the case. In fact, think about that. They sell hydrogen peroxide at CVS. If it decomposed to form hydrogen and oxygen, we would essentially be worried about selling people this explosive combination of gases when they break down. So instead, what happens when hydrogen peroxide breaks down is it forms a much more benign water and oxygen. When we balance this equation, we're going to get 2, 2, and 1. I hope you enjoyed that demonstration. In this demonstration, we're going to decompose sucrose, normal table sugar. Let's have a look. Hopefully you thought that was pretty cool. Let's take a look at the chemical reaction that occurs here. So we have sucrose, C12H22O11. Once again, we're going to expose it this time to a concentrated sulfuric acid solution, and it's going to decompose into two components. So we're going to have water plus carbon. And that was the black solid that formed as a result of this decomposition. If you notice, the ratio of hydrogen to oxygen in sucrose is the same 2-to-1 ratio that you see in water. And in fact, we're getting 11 water molecules from the decomposition of every sucrose molecule. We're also getting 12 carbon atoms, which are what are making up that black solid that formed. Let's take a look at another demonstration.
Okay, we're going to turn this off, turn that on.
KClO3, and we exposed it to a tremendous amount of heat energy. So first the potassium chlorate melted, and after that, we basically broke down that potassium chlorate into potassium chloride plus oxygen. Balancing this equation, we're going to get 6 oxygen, 2 potassium, 2 chloride, 2 potassium chloride. The second part of this reaction, when I dropped in the gummy bear, is basically a reaction between the sugar in the gummy bear, C12H22O11, and the oxygen that was produced as a result of the decomposition. But we'll talk about that later when we talk about combustion reactions in lesson 10. So now we're going to take a look at some examples of writing chemical formulas and equations for decomposition reactions. So in our first example, we have water. Water only has 2 elements. So the only thing that can happen here is we're going to break this down into hydrogen and oxygen gas. And then the only thing left to do there is to balance it. So we have water breaking down. We're going to need 2 waters to form 2 hydrogens and 1 oxygen gas. In our second example, we have mercuric oxide. So mercuric oxide is going to be another example where we break it down into its elements. So we're going to have mercury, which of course is a special element. It's the only metal element that is a liquid at room temperature. So we have mercury, and we also have oxygen. And remember the comment from last week, whenever oxygen is by itself, it needs this 2 down here because it's a diatom. So now we can go ahead and balance this. So we're going to put a 2 in front of both the mercuric oxide and in front of the mercury, and then a 1 in front of the oxygen. So just like we saw for synthesis reactions, there are different subcategories for decomposition reactions. And in fact, many of them are very similar but opposite to what we saw for synthesis reactions. Here's an example. In this case, when we have an acid and we heat it, it decomposes to form water and a non-metallic oxide. You might remember from when we talked about synthesis reactions, taking a non-metallic oxide and adding it to water created an acid. Now we're simply undoing that process. So what you want to do is look at your acid and then subtract water out from that acid. So if I have H2SO4 and I pull out the H2 and 1 oxygen to make water, I'm left with SO3. Water, of course, in this case is going to be a gas. SO3 will also be a gas. Anytime that we have heat and we have water as a product, we're going to assume that we've added enough heat that that water is going to be vaporized. Okay, balancing this equation, we'll wind up with all ones here. So we're going to have a 1 here, a 1 here, and a 1 here. We take a look at the next subcategory. Again, this is analogous to what we saw in the synthesis reactions, except now we're breaking that down. So we have a metal hydroxide. When it's heated, it's going to decompose to form water and a metal oxide. So in this case, we have calcium hydroxide. We're going to pull water out of there. So we have H2O. Again, it will be a gas because it's being heated. And what's left behind is CaO. One of the O's is there. The other O went to make water. So our second product is going to be CaO. We'll call that a solid because there's no liquid water to speak of in this. And finally, balancing this, again, we're going to wind up with coefficients of 1 across the board. There are 2 more subcategories of decomposition reactions. So the next one says that when we have a metal carbonate, like the very first demonstration that I showed you with cupric carbonate, that's going to break down to form carbon dioxide and a metallic oxide. So once again, we're going to pull carbon dioxide out of here. So we'll have carbon dioxide gas, and what's left over is calcium oxide, and that calcium oxide is going to be our solid. Now we're going to balance this equation. So we'll have 1, a 1, and a 1 here. And finally, with number 5, the last subcategory, the last type of decomposition reaction, we have potassium chlorate. That was that gummy bear demonstration I showed you. So you might remember from just a minute or 2 ago, when we look at that reaction, we're going to form KCl. That is our metallic chloride. And our other product, according to this, is oxygen. So KCl was that solid that was actually kind of shooting out of the test tube there. And now balancing this, we have a 2 here, a 2 here, and a 1 here. So now I'd like you to scroll down and look at some of these homework problems. We're going to try a few of them together, and then we'll finish the rest for homework. So once again, just going over the 3 different assignments that are out there. So my accelerated honors students, you're going to be predicting products and then writing a balanced chemical formula and then writing that out in Word format. For my honors students, you already have a complete chemical formula. I'm just asking you to balance it and then translate that into Word format. And for my college and career prep students, what I'm asking you to do is simply to write out the names for this and balance it. Okay, looking at our first example, we have an acid. So if you recall, an acid, when it breaks down, is going to form water and a non-metallic oxide. Again, we're not going to worry about states of matter here. So in this case, our non-metallic oxide is SO2. We can balance that by adding 1s in all of our spots here. And then finally, we're going to write out the formula for this. So this will be sulfurous acid. Breaks down, it forms water and sulfur dioxide. In our second example, we have water. So this one we saw earlier breaks down into hydrogen and oxygen as our only products. So we can write water breaking down into hydrogen plus oxygen. Remembering, of course, that both of these are diatomic, so they'll have 2's next to them. Then balancing this, we wind up with 2, 2, and 1. In our third example, we have silver carbonate, a metal carbonate. So that metal carbonate is going to form carbon dioxide as one of its products, so that's CO2. The other product is what is left over. So we have silver and one more oxygen, so we have silver oxide, so that's Ag2O. Balancing this, we're going to get coefficients of 1 straight across here, and then we'll write out the names. So we're going to start off with silver carbonate, breaking down to form carbon dioxide plus silver oxide. Okay, let's take a look at some equations in word format. So in this case, we have 3 different word format equations. So in the first one, we have hydrogen peroxide. So we did this as one of our demonstrations. We said that hydrogen peroxide broke down into water plus oxygen gas. So in our formulas here, we're going to have H2O2 breaks down into H2O plus O2. And then finally balancing this, we have 2, 2, 1. Just add those up here. All right, our next example is rather tricky. So what I'm going to do is I'm going to start off by showing you ammonium carbonate's formula. So we have NH42 CO3. So NH4 is positive 1, CO3 is negative 2. So we need 2 copies of the ammonium in order to balance this out. Now, in some cases, and this is one of those cases, it's actually easier to write out the chemical formula part first. So when this breaks down, it forms a couple of things. So carbonates are going to form carbon dioxide. So that's one of your products. The second thing is these ammoniums are going to break down to form ammonias, and there'll be 2 of them. And you'll notice that we have 2 hydrogens left over and 1 oxygen. So of course, that's going to make water. So in terms of our names, we're going to have carbon dioxide. We're going to have ammonia. And we're going to have water. And then balancing this. There are 2 ammoniums, so that gives us 2 ammonias. And the 2 hydrogen and 1 oxygen form 1 water. And then finally, carbon dioxide is pulled out of here, so we have 1 of those as well. You want to think about it like a picture. This ammonium carbonate looks sort of like this. So what ends up happening is we get this compound forming, here's an ammonia, here's another ammonia. We have 2 hydrogens and an oxygen, and then we have CO2. So if you imagine this part forming the CO2, and then what's left over is our water. That was a tricky example. Okay, let's take a look at our last one. We have potassium chlorate. So potassium chlorate is that same example we saw earlier. So we're going to make potassium chloride and oxygen gas. So potassium chlorate is going to be KClO3. It's going to break down to form KCl plus O2. Then finally, balancing this, we'll need a 2 in front of our KClO3. That'll give us 6 oxygens. So we put a 3 here and a 2 there, and we can just copy that up here. Okay, please attempt to do this homework. We'll review it in our next lesson. If you have any questions, please let me know. Thanks, everyone. Have a great week.